Assalamualaikum Mas Yosi.
Waalaikumsalam, Pak.
Mana kabarnya nih, Pak?
Ya, Pak. Sehat, Pak.
Udah ngumpul di STM KG ya?
Di pusat, Pak, sekarang, Pak.
Oh, di pusat.
Iya, betul, Pak.
Di apa?
Di Geopot.
Oh, di Geopot.
Geopot.
Sama Mas Fajri ya?
Fajri, ya, satu ruangan Pak Fajri. Beda bidang.
Oh, beda bidang. Sampean ikut bidangnya sama Pak Ariska?
Pak Hendra, Pak.
Oh, Pak Indra. Oh, pada waktu ya. Ini ya. Iya.
Sehat, Pak Wadi?
Alhamdulillah sehat, Mas.
Alhamdulillah.
Ini nyambi rekon. Morning, Master.
How are you? Good to see you. Good morning. Hey,
Good morning.
John. Good to see you, John. Good evening, John.
Good evening and good morning.
Right. Both.
Yeah, good morning, Walter. Good morning, Mr. John.
Good morning.
Yeah.
It's early for you, only 8 o'clock. Very early. How are you, Emanuela?
Good morning, Mr. Walter, Mr. John, Miss Donna.
Yeah, good morning, Miss Pak Jati.
Yeah. Okay. Good morning, Mr. Suwardi.
So you got to bed quite late last night, John. No, the night before, I guess.
Night
The
before.
one that
it
you
was a
went to
little
1
late.
o'clock.
Yes, indeed.
You're in Chestnut Hill now?
No, I'm actually in Rochester, New York.
Rochester, oh. How's the weather?
It was beautiful today. It was about
good.
80 degrees Fahrenheit. There was rain to the north of us, rain to the south of us, but we just got a few drops. That was it.
Wow. Whatever became of Kodak?
Kodak did not survive the transition to digital films, but the Eastman name is still very big here in Rochester.
Right.
In fact, I think tomorrow my wife and I and friends are going to go over and view the Eastman estate, which is supposed to be quite interesting.
Oh, wow. Quite interesting, quite extensive, I imagine as well.
It's big. I guess there's an art collection there. The grounds are supposed to be very pretty. House is supposed to be quite interesting.
Do you have a garden at home?
Oh, that's a tough question. In theory, yes, but I think the weeds are happier than the plants we planted.
Oh, okay. Well, weeds are beautiful too.
They can be.
Well, you get wildflowers.
Yeah, they can be pretty wild. But yes, no, we're visiting actually a college roommate of mine from
Oh, I
Harvard
see. Oh,
in
okay.
Rochester. So he and his wife are actually both MIT PhDs, and
Oh, what field?
he got his PhD in metallurgy engineering, and she got her PhD in chemistry.
Two good topics, very highly employable people.
Two very relevant topics in today's society, no question about that.
Metallurgy, yeah, and chemistry. Wow, perfect.
Yeah, they lived for years in New Jersey and worked for She worked for Bell Labs. He worked for Western Electric.
Yeah.
It was an AT&T spinoff, then they moved to Rochester, and he got a job in working in the Science Museum here in Rochester.
Oh, lovely.
And
Well, he'd be
he did
good.
that.
Good
Yeah,
background.
He did that for a few years. Was excellent background, and then he retired about a year and a half ago.
Did Bell Labs close down or shrink?
They shrank tremendously. Yeah, I don't think they completely closed down, but they got into much more applied things and much smaller.
I see. So good morning, Jim Morey.
Good morning.
There you are.
Raining in Kyoto this morning.
Oh,
Is it
well,
hot there?
you get a lot of rain in Kyoto. Well, you get a lot of rain in Japan in general. That's why it's so green.
It was the rainy season was supposed to end about a week ago, but it didn't.
Oh, a week is not a long time to be shifted, really. When you fly over Japan, you realize it's actually a pretty big country. Just a lot, not much of it can be occupied. Between the mountains, you get these areas where you can have a settlement, and then you have to go past several other mountains, and you get another settlement. Habitable. The habitable land is only a percentage of total land area.
Right, it's maybe I think 10% or less. So it tends to be the flat coastal areas, which tend to be sedimentary basins, which means that site response is a very important issue.
Why is the west coast of Japan economically lower than the east coast?
West, you mean the northwest side, the Japan Sea side, you mean?
Yeah, Japan Sea, like Totori.
I'm not sure. I mean, traditionally, the population centers have all been on the Pacific side, the big population centers.
Yeah.
And that's probably because of the shipping and there's more flat land. The weather's better. It's very cold in the winter on the Japan Sea side. So people just tend to live more on the Pacific side than on the Japan Sea side.
It always seemed to me that if you wanted to have a piece of land and a nice big house and relaxing life, living on the Japan seaside would be very attractive, like turning back the clock 100 years.
Except in winter.
Oh, I didn't know. Nobody told me about the winter problem. Cold and windy.
Yeah, a lot of snow.
Oh, a lot of snow too. Well, that can be nice. You're from Chicago. You know about snow. It's not. What's wrong with snow?
Yeah, so I used to say I like snow, but recently I don't know if I could really withstand a cold Chicago winter or not.
Yeah, well, you've been out of Chicago for 50 years, so it take a little acclimation to return there. John never left it. John, born and raised in Massachusetts, still there, toughing it out.
I was raised in the Midwest. I was raised in St. Louis.
That's what I said, toughing it out.
and I was actually born in the Philippines.
Oh, born in the Philippines. Oh my goodness. Wow.
Yeah.
Well, it's a history that I think you probably told me while we were traveling together in China, but I forgot the interesting details. Yeah, now the St. Louis part, now I remember. Yeah. So Jim and John, my wife and I were watching a Woody Allen movie from 1975, Annie Hall, with New York City people and their behavior, and everything seemed normal. You know, all their all their eccentric behavior. Yeah, that's about right. You kept thinking, yeah, that's about right.
Yes, indeed.
Okay, Madonna, I guess probably we can start at 6:05 at 8:05, or what would you like to do?
Yeah, maybe it's okay if we direct start right now.
We have
So,
31 people. It will come up to about 44 at the peak.
yeah, I think I will other participants come to this this class. I think it's okay if
Yeah.
we can start right now.
Okay.
It's okay, Mr. Walter. Yeah, please, Miss Yossi, turn on you.
Okay, so we can start now. Okay.
Yes.
Okay. Assalamualaikum warahmatullahi wabarakatuh. Good morning, everyone. May I have your attention? Our course is about to begin. I am Yosi Setiawan, the moderator of today's course, and I'm very pleased to see you here and welcome all of you to this course. And today is the last day, and I hope everyone is still excited to join this course. So today we have 3 sessions. The first speaker is Professor John Abel from Boston College, USA, who will talk about depth to bedrock and Hvsr. And the second speaker is Professor Jim Mori from Kyoto University, Japan, who will talk about using microtremor to determine site response. And the last speakers are Robbie Walansha and Dr. Sigit Pramono from BMKG, who will talk about earthquake force design, ground motion SNI of Indonesia. Now let me introduce the first speaker, Professor John Abel. He is Professor of Earth Science at Boston College and the Western Seismological Observatory, and he is a graduate of Harvard University in BS and Caltech in PhD. He has extensive experience as a seismic network operator and data analyst. He is the author of numerous journal publications and recently released his book entitled New England, USA Earthquakes. He has served as a long-term editor of the Seismological Society of America Journal, Seismological Research Letters. He will talk about depth to bedrock and Hvsr. Now, please allow me to welcome the speaker, Professor John Abel, to deliver his presentation. So, Professor, you have 50 minutes to talk, and you can finish at 8:55. Then we will continue to the second speaker, Professor Jim Mori. And after that, we will have discussions for both presentation for about 10 minutes. Okay, Professor, the floor is yours.
Thank you very much. I'm going to share my screen. Okay, so you should be able to see the title slide from my PowerPoint. And I'm going to be talking about estimating ground shaking, amplification potential using Vs30 and H/V spectral ratios of seismic noise. The topics that I'm going to cover in this presentation are the following. I'm first of all going to summarize actually material that was presented on 2 days ago, effect of strong earthquake ground shaking on man-made structures. And then I'm going to talk about ground shaking amplification due to superficial soft soils. I will talk about VS30 and ground shaking amplification. And then I'm going to talk about H/V spectral ratios, or what sometimes or many people are now calling the Hvsr technique, and how it relates to earthquake ground motions. I'll talk about measuring H/V spectral ratios using ambient seismic noise. And then I'll say a few words about modeling H/V spectral ratios and what can be learned from that. So to begin with the first topic about how structures get affected by earthquakes. For the earthquake engineers, a building that's standing and gets shaken at its base, the building acts like a damped harmonic oscillator, which has some mass, M, shown here. And of course, the mass of the building is up above ground level. The structure of the building acts as a spring with some spring constant K. And the building is not purely elastic. It has some damping. It has some capability of absorbing deformation energy. And so the damping of the building is quantified here by this dash pot, and the letter C indicates damping. The period of the natural period, rather, of the building is related to the natural frequency of the building, which depends upon its height, depends upon the mass, and then the damping depends upon the mass and the spring constant, but also on the behavior of the dash pot, the ability of the building to absorb energy. Buildings are built very strongly in the vertical direction, but they're not so strong in the horizontal direction. So therefore, it's the horizontal component of ground shaking that is of the greatest threat to man-made structures. So each structure, like a building, has a set of natural periods at which it wants to vibrate. The largest vibrations will occur at what's called the fundamental period or natural frequency of the structure. And the very rough rule of thumb, which I believe Professor Jim Morey mentioned a couple days ago, is that if N is the height of the building in stories, so if the building simply has one floor, it's a one-story building, N is 1. If it has ground floor and then one floor above that, or 2 floors, then N is 2. The fundamental period of a building is approximately N over 10 in seconds. So a 2-story building would be 2 over 10 or 1 over 5 seconds, 0.2 seconds. And that's important because that means different structures, depending upon their height, are going to shake at different frequencies or different periods of ground motion. So another slide shown by Professor Morey. What we have here is the spectrum of horizontal acceleration on the top for, let's say, a magnitude 6.5 earthquake recorded at 25 kilometers epicentral distance on hard rock, on soft rock, and on soil. And the period of, for instance, a 2-story building is about 0.2 seconds. So here's the shaking for those different periods of ground motion. If you have a structure that's about, let's say 5 stories tall, in this case, a freeway bridge, it's going to be shaking at about a period of 0.5 seconds. And so you can see that the soils are going to amplify the ground shaking quite a bit. For a 20-story tall building, here's where the shaking is. And then when you get to the world's tallest buildings, the natural period is going to be 10 seconds or more. if you have soft surface soils, they can modify the amplitude and the frequency content of the ground shaking compared to the ground shaking you would experience or you might record with instrumentation on nearby bedrock sites. I say modify the ground motion because sometimes the ground motion gets amplified by soft soil. Sometimes it actually gets de-amplified by strong ground motions, and that depends upon the strength of the ground motion and the period or the frequency of the ground motion. So different soils will modify the ground shaking in different ways. So here's an example, a very famous example from Oakland, California, just across the bay from San Francisco, California, of destruction in the 1989 Loma Prieta, California earthquake, a magnitude, about 7.1, 7.2 earthquake. So there was a major freeway that collapsed that caused loss of life. The collapsed section of the freeway was right here in this white area on very, very soft, what they call bay muds. And a strong motion instrument that was recorded that recorded earthquake ground motions on that site recorded very, very high amplitude, very, very long duration ground shaking. A part of that freeway that did not collapse, although did take some damage, was on this kind of tan area here, which was sand and gravel. And here's what a seismogram or accelerogram from that area looked like. And it was lower amplitude, somewhat less duration, but still some shaking of the amplified shaking of the ground motion compared to a recording on bedrock, which is this darker tan color right here. You can see very low amplitudes and much shorter duration ground shaking. So the soils will very much amplify the ground shaking. Here's another example that was also discussed 2 days ago, Mexico City, 1985. In the 1985 earthquake, which was centered about 200 kilometers away from Mexico City, the ground shaking was strongest at about 2 seconds period, which means buildings about 20 or so stories were shaken most strongly by the ground shaking. And that amplified ground shaking was preferentially experienced on structures that are built on the old lake bed, filled in sections of the city on the old lake bed where Mexico City is built. Hard rock sites in the hills away from Mexico City experience very much weaker ground motions, and the very long 2 second period waves generated by the earthquakes but trapped in the lake bed sediments are shown here. And so it was the tall buildings that preferentially collapsed, the taller buildings, 20 to 30 stories in Mexico City. 371 such buildings collapsed. People who were in very short buildings, let's say with just a single floor or maybe 2 floors, experienced no damage at all. They barely, in some cases, barely felt the earthquake. So below is a spectral seismogram. Actually, this is a response spectrum for the earthquake shaking in Mexico City. The solid line is the observed spectral ground shaking. The dashed line is what was expected prior to the earthquake, and amplification at about, well, roughly 2 seconds. And so resonance period, anywhere from 10 to 15 to 20 story buildings were most strongly affected. So if we look at the spectral acceleration divided by the maximum ground motion, the blue is what was experienced on bedrock conditions. And you can see at, let's say, 1 second period, the level of motion is here. When you get to stiff soil or soft rock or stiff soil conditions, now you're at the green curve. When you get to deeper soils, then you get to this curve up here. And the softest soils of clay and sand actually had ground motions like this. You can see that at these the shorter periods, the ground motions were de-amplified, but they were amplified at these longer periods. So that's why I talk about ground motion modification, because the ground motions were not amplified at all frequencies or all periods in the softest soils. In fact, they were de-amplified or only moderately amplified at very short periods. Now, in order to construct buildings, you have to know how much amplification, or have an estimate of how much soil amplification there might be. And a few decades ago, I believe it was in the early 1990s, the geotechnical engineering community came up with a parameter called Vs30, or the average shear wave velocity in the top 30 meters of soil. So from the surface down 30 meters, in imperial units down 100 feet. Take the average velocity in that soil column, or in that column of earth materials, and that gives a parameter that can be used to give an estimate of how much ground shaking there might be. And the design of buildings then is controlled by that amount of amplification for the soils. So rock and soils are divided into different classes based on their Vs30 values, and different classes of soils then must be designed to different strengths or different resistances to seismic shaking. So here are the classifications for what's called the National Earthquake Hazards Reduction Program site classes. Site class A is the one where we expect the least amplification, and that's basically hard rock greater than 1,500 meters per second for Vs30. Site B has Vs30 in this range, 760 rather to 1,500 meters per second. Site C is 360 to 760 meters per second. Site D is even softer soils, 180 to 360 meters per second, and very unusual soils with Vs30 values less than 180 meters per second are called site class E. Now, how much amplification do these different Vs30 values correspond to? Well, if we have an earthquake ground motion that on rock has a peak acceleration of 1/10 of a g, 0.1 g. So this red line here starts at 0.1 g. Well, as the Vs30 reduces, the short period amplification, the amplification of the seismic waves at about 0.1 or 0.2 seconds period starts increasing. And it increases by more than a factor of 2, more than doubles the amplitude on the soils, the top of the soils, compared to what would be observed at bedrock. And so then if you have stronger ground shaking, for instance, if the ground shaking is 0.4, actually at those short periods, the ground motion is de-amplified due to what are called nonlinear soil effects. So the ground shaking modification is very complicated because, as you can see, it depends upon both the period of the ground shaking as well as on the amplitude of the ground shaking. But in general, lower Vs30 generally at short periods is going to correspond to higher amplification. Going back to that Oakland, California site, the geotechnical engineers, after the Loma Prieta earthquake, went to the areas of the Holocene muds and the older, firmer sediments and did boreholes and measured S-wave velocities on those boreholes going down to 30 meters. And you can see that on the hardest materials, the sands and the Pleistocene alluvial fans, which is mud and dirt and rock that's come off the hillsides, the Vs30s are somewhere around maybe 350, 340, 330 meters per second. When you're in the alluvial, the youngest alluvial fan material, it's maybe 220, but you get into those very young bay muds, and VS30 is going to be more like maybe 110 or 120. You average all of these together, you get the dashed red line right here. So VS30 has to be a very, very site-specific measure or estimate, and that's then used for design of structures and used to estimate how much ground shaking amplification there might be in those structures. So for the seismic provisions in the United States and the NEHRP provisions, they have tables like this where you have the site class A, B, C, D, E. You have the period of the shorter period ground shaking, longer period ground shaking, and amplification factors. And the amplification factors for site class E get up to 3.5 compared to, let's say, the normal rock conditions. So these would be numbers that engineers would use when they were designing structures. Now, as a seismologist, my interest is, how do you determine VS30? And there are several different ways to do that. One is to conduct seismic refraction profiles. The best way to do it is to do an S-wave seismic refraction profile. That can be a rather challenging exercise compared to determining P-wave seismic refraction profiles. So perhaps one way to do it is to do a P-wave seismic refraction profile and then make some measurements to make an estimate of the ratio of S-wave velocity to P-wave velocity. There is another method that is now getting to be more commonly used, MASW, which is measuring putting out a string of seismometers and then measuring the propagation of surface waves along the profile, getting a dispersion curve of the surface waves. Typically, they're going to be Rayleigh waves, and then inverting that dispersion curve for seismic velocity with depth. That will tend to give you the best resolution of the seismic velocities at the shallowest depths, and then the velocities, the resolution on the velocities becomes worse as you go down to deeper depths. Many geotechnical engineers prefer to drill holes and then do what are called cross-hole S-wave surveys, where you have S-wave detectors in one hole, you have S-wave sources in the other hole, and then you're sending energy across, and that is doing kind of a sort of a tomographic type estimate of the S-wave velocity with depth. That is much more expensive than the two geophysical methods, but it certainly gives you very, very good ground truth at all depths at which you have your borehole. And then it can S-wave velocities can be inferred indirectly from geotechnical borehole data, for instance, from standard penetration tests. What I want to do is I want to spend some time talking about the so-called Hvsr, or horizontal to vertical spectral ratio method, because this one is becoming more and more popular. It's been used now by seismologists for easily 2 decades or more, but more and more engineering firms are actually getting involved in making Hvsr measurements also. And the idea is the following. You go out and you put a seismic monitoring instrument that can record a broad band or a fairly wide band of ground motion frequencies, from very low frequencies to very high frequencies. And then you just put the instrument out for maybe 10, 15, 20 minutes, and you measure ambient seismic noise. You just, whatever the seismic noise is, you have no active sources. You just put the instrument out, and then you let it sit. And then you process the records, the horizontal record, the horizontal seismogram, the vertical seismogram, through a Fourier transform. Now you have a spectrum of the vertical, of the horizontal rather than of the vertical, And then you divide the amplitude spectrum of the horizontal by the amplitude spectrum of the vertical. And it turns out that shows you frequencies at which the soils seem to be resonating. This is called often called the Nakamura Method, which is and that's because it's named after the Japanese engineer who first proposed it. And this has now been very, very widely used in many, many different places. And there have been a lot of studies that have been done of the Hvsr method as well. So the method was introduced, as I said, by Nakamura in 1989. There has been a lot of testing and basically some specifications that have been put together on how to do Hvsr measurements, put together by a group in Europe that goes by the acronym SESAME, S-E-S-A-M-E. Now, when you're recording ground noise, just natural ground noise, you put the instrument on and just let it sit, record the ground noise. The lower frequency ground noise is going to be what we call microseisms, and that will be energy below about 1 hertz in frequency. And this is energy that is caused by, for instance, ocean waves. It's caused by tidal motions in the oceans. And the microseisms are actually Rayleigh waves that are propagating from the seashore inland. So in many places where you're relatively close to the ocean, I'm close to the ocean in New England, where I work and live. You folks in Indonesia obviously are all going to be close to the ocean as well. Above about 1 hertz or maybe half a hertz are what we call microtremors. They're also natural noise, but they're a combination of natural noise generated by the wind and maybe by flowing water and streams and things like that, but also anthropogenic noise. For instance, automobile traffic, industrial vibrations, industrial machinery, even people walking if you're working in an urban environment. And microtremors are composed of surface waves as well as body waves, whereas the microseisms are almost exclusively surface waves. And for the Hvsr method, you need to have 3 component measurements. You need to have both the vertical and the horizontal component measurements. The idea of the method is really very simple, as Nakamura first proposed. So let's say you have a soft soil layer here on the left with some average velocity Vs, underlain by a much harder layer. So the seismic energy, if it gets up in the soil layer, will tend to bounce between the free surface, the Earth's surface, and the interface between the harder material and the free surface. And as it bounces up and down and up and down, it gives you a resonance peak on your seismic instruments at the surface. And just ambient ground noise will get trapped and bounce just as earthquake waves will. So here is a spectral ratio, horizontal to vertical spectral ratio, showing a peak at a frequency, and then there's another peak at a frequency here. The lowest frequency peak is going to be the fundamental resonance, and that the frequency of that peak F is going to be related to the soil parameters by this equation right here, where Vs is the average soil velocity and H is the thickness of the layer. So Vs over 4H. For shear wave, for different kinds of materials, they're going to have different shear wave velocities. If you have very, very unconsolidated clays and you have, for instance, landfill or turf, shear wave velocities in those materials will be as low as 100 meters per second. If you have natural clays that are of good quality and you have maybe silts with some sand in them, the S wave velocity might average around 200 meters per second, be a little bit faster. If you get into sands and gravels, which are themselves very hard materials, but maybe loosely put together, the S wave velocity will be up to maybe 300 meters per second. When you're into gravel, and that includes maybe large cobbles, and you have weathered rocks within maybe a sandy matrix, now 400 meters per second. And by the time you get into maybe somewhat eroded, but more or less competent sedimentary rocks, 500 meters per second or more. What bedrock, even if it's unweathered, will have S-wave velocities easily above 1,000 meters per second, and perhaps even a couple thousand meters per second. And so if you have very soft soils over a very hard bedrock, which for instance I work with in New England, you get very strong resonances and therefore very strong peaks in the Hvsr curves that get determined from ambient seismic noise. Now, if you know the so-called peak frequency, this FF, FR here, FF, or FHV here, if you know this frequency, then by this equation right here, you can compute the average S-wave velocity to that interface if you know the thickness h, and it's simply 4h times that frequency. If you know the average surface velocity, or have an estimate of your average surface velocity, divide that by 4 times that peak frequency, and that will give you an estimate of the thickness of the layer that's shaken. And of course, you know, you have to have some a priori knowledge of either the average Vs or of the thickness of the layer in order to make these estimates if you have the measurement of your fundamental frequency F. So let me show you a little bit about how such measurements get made, Hvsr measurements. So this is a site that we put out near the Boston College campus. It's actually just off the edge of a man-made reservoir, a man-made dam rather. And we were making Hvsr measurements on the dam as well as here. You can see the bedrock is behind me and bedrock is just right below the surface here. We have a black recording box here. There's a seismometer that's maybe, I don't know, 10, maybe 12 centimeters high and maybe 8 centimeters in diameter. And we put it under this box in order that the wind doesn't shake the seismometer. It's just getting the shaking of the ground. And then we have a battery that it's run off of. And here I am for scale. And we recorded for about 30 minutes. We're working with a group from the US Army Corps of Engineers, and they use a different instrument for collecting ambient seismic noise for Hvsr measurements. They use the so-called Trimino instrument right here. This has three component seismic set of seismic transducers, velocity transducers in it, as well as 3 component accelerometers. It has GPS. It has a wide range of recording. And the Army Corps of Engineers has used this instrument, and we've actually compared our system to their system and gotten virtually identical results. Now, you go out, set the instrument out for 20 minutes, you get your seismic noise. Now you want to analyze the seismic noise to get the H over V spectral ratios. What do you do? How do you do that? What software do you use? Well, if you purchase a Trimino instrument, the company that produces that will provide a set of programs for you called the Gorilla analysis package that will do the Hvsr ratios. The group in Europe, the Sesame group, has a package that includes data analysis systems, data analysis rather software. And here's a website for the Sesame package. I actually wrote my own in MATLAB, and one of my students is now doing a PhD at Tufts University. He took that with him and he's modified it. So you can actually, I mean, the method is simple enough that if you want to program it up on your own, you can actually do that and then do the spectral ratios. So here's an example of what you get. These are real data. On the bottom, you have the individual spectra. The vertical is the lighter purple color. This blue is one of the horizontals, the The green is the other horizontal. And then if you divide each of the horizontals by the vertical, you get, and then add them up, in this case is what they did, you get this kind of H over V curve. And it's got this strong peak. Here's 1 second period, 2, 3, I'm sorry, 1 hertz rather, 2, 3, 4, 5 hertz. Roughly at 5 hertz is the spectral peak. There's another spectral peak here, but I think that that's an instrument problem. And then the Gorilla software, which is where this slide came from, gives you some spectrograms as well as estimates of the azimuth of the energy with frequency. The Boston College processing software provides outputs like this. Again, 1 hertz, 10 hertz. You see there that this particular set of seismograms all have a peak at 10 hertz. And I'm showing you 4 here because these were observations taken on different days at exactly the same site, which shows you how stable these spectral ratios really are. Here's a number of measurements taken at the same site on the Chestnut Hill Reservoir. And each of these is a spectral ratio. You can see that there's quite a variation in the amplitude of the peak, but the frequency of the peak is basically identical. And so the method is very stable for getting the peak frequency, but the amplitude or the amplitude of the spectral ratios can vary by quite a bit. Now, just to show you what happens if you have a site on rock, so that site where I was sitting on the bench before, which is right here, here's the spectral ratio for that. You'll notice that there really is no peak. There's a kind of a slight increase in the spectrum here, but right around somewhere in here is where the data become unreliable at higher frequency. So these are unreliable here. So this is a flat response. That's what we expect for a rock site. We go here, which is now on the middle of the dam, of the dam that holds back the Chestnut Hill Reservoir, and now there's a very strong peak at about 10 hertz, 9.775 hertz is what's measured. So we went from the rock up here all along this dam. The dam is highest right about here, and then it gets shallower, 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 shallower. And by the time we got to here, which was the last point of our survey, now we were actually back to ground level. There was the dam was ended there. And here's what we get. So where the bedrock is, we saw no peak frequency at all. The peak frequency is the lowest where the dam is the highest, and then it gets higher and higher frequency, which corresponds to shallower and shallower, or thinner and thinner and thinner layers. Just what we would expect from the theory that I discussed earlier. And when we go and remeasure the peak frequencies many, many different times at the same site, we have a couple unusual observations, but for the most part, the peak frequencies have relatively little scatter. The scatter here looks greater than the scatter here, but in terms of percentage, this percentage in frequency, because this is a much higher frequency, is about the same as the percentage change down here. So the method is very, very stable, very, very reliable. I want to finish by talking about modeling Hvsr data, because of course, we want to be able to go both ways, make measurements, infer what's in the soils. But if we have information about the soils, let's say from geotechnical data, we would like to estimate what the resonant frequencies are going to be, because the resonant frequencies then are things that we can go out and measure, and we can see if we have a good correspondence between the soil column measurements and the soil column. I'm sorry, the estimates of the peak frequencies from the modeling, and then what we actually observe, because it's very easy to take these measurements, sit for 15 minutes, go to a different place, sit for 15 minutes. So if you have some boreholes, you can start your analysis there and then make your ambient noise measurements as far away as you want, and you can calibrate back to where you have the good soil columns. We use two programs. One is called NRADL, and this models SH waves reverberating in a soil column from a strong reflecting surface. And this was written by David Bohr of the U.S. Geological Survey, published in the year 2000. If you Google NRADL and Bohr USGS 2000, you can find this code, and it will give you synthetic seismograms that look something like this right here. I'll show you another example later. The other code is a code called HVINV, and this was published by Garcia-Jerez et al. In 2016. And this code actually assumes that you don't just have propagating S waves, but you actually have propagating P waves, S waves, as well as Rayleigh waves in the soil column. So it does a much fuller computation of the ground motions, and then from that you can get an estimate of the H/V spectral ratios. So we did some tests with each of these two codes, and I just want to show you a little information about those tests. So this is a seismic velocity model that we used. The model was derived based on some data actually from a earth embankment levee along the along the Rio Grande River in Texas. And so the thicknesses are in meters, and this goes down to about 29 meters. P wave velocities are shown here with an increase in P wave velocity with depth. S wave velocities are shown here. So you'll notice 135 to 260. So we're in very soft materials at the top, getting into more competent materials at the bottom. You also need an estimate of the density of the soils in these programs. And so we estimated densities based on some a priori information that we had, some independent information that we had. So here is the NRADL spectrum that came out of that came out of the NRADL program using that velocity structure that I showed you in the previous slide. And there's a fundamental frequency at 1.992 hertz. There are some peaks up here at 5.465 hertz and at 8.919 hertz, and these are actually higher mode resonances of this fundamental mode here. We also ran this exact same model with the HVINV code. And you can see right here, the fundamental frequency is very close to what it was on the previous slide. The previous slide is 1.992, here it's 2.058, so almost exactly the same. This code also gives some higher modes of propagation, but they're much lower amplitude than for the NRADL code. And I think that this is reflecting the fact that this has PS and Rayleigh waves in it, whereas the NRADL code only is using SH waves. But if you want to get an estimate of what the frequencies are going to be of the different, if you put a measuring instrument on the surface, this is these codes do very, very good job of predicting what the frequencies are going to be. The big problem we have with the Nakamura method, and this has been has been acknowledged since the time of Nakamura, is that the amplitude of the ground shaking amplification cannot be determined from the Nakamura method, only the frequency of the resonance. And of course, the frequency of the resonance is important to know, because if you have a resonance of 2 hertz, let's say, which is 2 hertz is about 5 seconds period, and you have a structure that is of 5 stories, that means that there will be amplification in the soils, significant amplification at the resonant frequency of your structures. So these resonant frequencies are extremely important to know for engineering purposes. We did some tests with that model I showed you earlier where we ran both of these codes, and we then decreased the velocity in layer 1 by 10%, decreased it by 20%, 30%, 40%, 50%. Then we increased it by 10, 20, 30, 40, 50%, ran the spectral ratios. We did the same thing by decreasing and increasing the velocities in layers 2, 3, 4, and 5. And when we did this, we found small changes in the peak frequency for the change in layer 1, layers 2 and 5, somewhat greater changes. But the greatest changes in the peak frequency were in layers 3 and 4, which are depths of 9 to 25.5 meters. And that's important because for instance, for the levee or for the dam that I showed you at Chestnut Hill, these are the places where you don't want to have failures. So you want to have the most accurate information about the velocities at those depths. As I said, the biggest problem with the Hvsr method is that you get information about the frequencies at which amplification will occur, but you don't get good information about excuse me, the amplification itself. So my time is just about up, but I'm at my conclusion slide. So first of all, to reiterate, a topic that was discussed a couple nights ago and was discussed last night. Man-made structures are sensitive to both the amplitude of a seismic ground shaking as well as to the spectrum of that ground shaking. And each structure has a natural period of shaking to which it is most sensitive. And therefore, any information we get on not only the amplitude, but on the period of ground shaking is important in order to figure out how to design structures to withstand earthquake ground shaking. Current earthquake building codes relate ground shaking amplification potential to the so-called S-wave velocity in the first 30 meters below the ground surface, which is called VS30. And there are a number of different ways to estimate VS30. It's even possible to make a rough estimate of VS30 if you have the peak frequency from an H over V spectral ratio. H over V spectral ratios of ambient seismic noise can give information about the periods or frequencies at which ground shaking amplification is likely to experience its greatest at which ground shaking is likely to experience its greatest amplification. And you can figure out H over V ratios by making measurements of seismic ground noise for maybe 10 to 20 minutes and then analyzing that with one of the programs that's available. Thus, this is a very fast, easy method with modern instrumentation and software to really, if you want to do a reconnaissance over a very large area, to estimate which areas may be prone to having the most damaging ground shaking. And then there are programs to model H over V spectral ratios or HVSRs. And these can be used to really work back and forward between what's known about ground motions and what's been measured out in the field to help refine estimates of where ground shaking amplification may most strongly occur. So with that, I end the slideshow and I thank you very much.
Okay, thank you, Professor John Abel, for the informative and interesting presentation. And now please allow me to read the summary on your presentation. So from your presentation, I can summarize that the man-made structures are sensitive to both the amplitude of seismic ground shaking and to the spectrum of that ground shaking. And each structure has a natural period of shaking to which it is most sensitive. And then the current building codes relate ground shaking amplification potential to the average as wave velocity in the first 30 meters below the ground surface called Hvsr. And there are several ways to measure the Hvsr. And then the H per V spectral ratios, or HVSRs, of ambient seismic noise can give information about the periods or frequencies at which ground shaking is likely to experience the greatest amplification. And the ambient ground noise and its analysis to HVSR is fast and easy with modern instrumentation and software. And the last is the program to predict HVSR from seismic models exists and can be used to estimate the spectral periods or frequencies at which ground shaking amplification is most likely to occur. Okay. Now coming the second presentation from Professor Jim Mori. So the discussion for Professor John Abel we will do the discussion after the presentation from Professor Jim Mori. So the second presentation from Professor Jim Mori. Professor Jim Mori is Professor of Seismology in the Disaster Prevention Research Institute, or DPRI, of Kyoto University. He is a graduate of Oberlin College, USA, and Columbia University in PhD. And prior to join DPRI, he worked in Papua New Guinea and at the USGS in Pasadena, California. Professor Mori has extensive research experience in Indonesia. He is the author of more than 75 publications and has lectured in many parts of the world. Professor Mori is the past president of the Seismological Society of America and is a fellow of the American Geophysical Union. Today, Professor Mori will talk about using microtremor to determine site response. Okay, Professor, there is some change in the schedule. You have 46 minutes to talk until 9:30, and then we will have some speech from Pak Supri, the acting director for Center for Research and Development. Then we will have discussion for 10 minutes. So yeah, Professor, the floor is yours.
Okay, did you say 9:30? So just 30 minutes.
Yes, 30 minutes, 36 minutes, yeah.
Okay,
Okay.
that's fine.
Until 9:30, yeah.
Let's see, can you see the PowerPoint slide?
Yes, you can see it clearly.
Okay, good. So I'm going to talk about site response. And actually, my talk is very, very similar to John's talk. But that's okay, because I think important information, if you hear it twice, you'll remember it better. So I'm going to cover very similar topics about site response and measuring site response. Just as an introductory slide, this is the Yokohama region. This is 5 kilometers. There's many stations in Yokohama, but if we look at this one station up in the mountains, this green circle, and one station near the coast, this red circle, here's the green station, here's the red station. The amplitudes near the coast are much, much bigger. There may be a factor of 10 or more from these two sites for an earthquake that comes from pretty far away. So we should be measuring about the same waves, but the site amplification really changes the amplitude at these two sites. So we've heard many examples of this. And I should just mention, so this is maybe a factor of 10 or more, 10 or 12, which is big. A couple of days ago, we talked about the difference between a magnitude 8 and a magnitude 6 earthquake close in, and the difference was only maybe a factor of 3 or 4. So in that sense, site characteristics can be much stronger than even the difference between a very large and a moderate size earthquake. We heard a lot about Mexico City already. In California, there's a place called Tarzana. And when I was with the USGS, whenever there was an earthquake in Southern California, it always shook the hardest in Tarzana. Well, at least the strong motion record in Tarzana was always the largest amplitude. So for example, from the Northridge earthquake, it had amplitudes near or over 1G for almost 7 or 8 seconds, with a peak of about 1.78 G. And that was maybe 3 to 7 times greater than a nearby site about a kilometer away. So there was a lot of studies done on this unusual site, and they measured the velocity, they measured the topography, and both those things apparently affected it. And as far as I know, there's actually no really good explanation or a complete explanation for why this site always shook so hard. These amplifications due to topography and velocity were maybe about 3 or 4, but it was always much, much stronger, the shaking. If we want to look at the spatial scale, the spatial dimension or the spatial variations, here's a good example from the Kumamoto earthquake in Japan. And these are results of damage, building damage investigation. And the colors show the percentage of collapsed buildings. So the orange and red show areas where it collapsed, maybe 80 to 100% of the buildings were collapsed. The blue and green is 0 to 10 or 20% of the buildings were collapsed. So this is looking at thousands of buildings. So I think this is a very good average compilation of the damage. And we see changes on the order of, let's see, about 100 meters or less. This is 500 meters. So changes at, anyways, smaller than a kilometer, maybe 200 or 300 meters, there's very strong variations in the difference of the damage. The other day, Ralph said that source effects could be very detailed on the order of maybe less than a kilometer. In this particular case, we think this is mainly a site effect. And the reason is, here's an old map from 1903 of the rice field distribution. And you can see a very good correlation of the rice fields, these gray areas, and the strong shaking, these red areas. And as you probably know, rice fields are flooded every year, and so they're very soft soils. There's no water there anymore, but there's probably lots of very soft sediments. And so in this case, it looks like there's a very good correlation between the areas of strong building damage and the areas of the old sedimentary rice fields of that area. And again, these variations are over maybe a few hundred meters. So they can change very quickly, both the site characteristics and the damage. Okay, one more example from Turkey. And you can see at this place, this building stood up, but the rest of these buildings all collapsed. And actually, the reason really isn't clear. I mean, maybe it's a construction problem, but it seems most people think it probably was a site contributed. I mean, this site is on a little bit higher area. These are sort of lower, more softer soils, probably. So we don't know yet. This is something that really should be investigated, but it seems that there was a very strong difference between this place where this building stood up and down here where these 1, 2, 3, 4, 5, 6, 7 buildings collapsed. Okay, as John mentioned, softer sites, lower velocity sites tend to have more amplification. And there's a lot of complicated effects, but sort of very simple linear explanation is just what's called the impedance contrast. Just a very simple measure of amplitudes in ray theory that is given by the amplitude is the density times the velocity. And so the impedance contrast is that ratio, and you take a square root. So in a very simple linear explanation, the velocity times the density, that contrast gives you the linear difference in the amplitude. And so for a very simple example, If we talk about a vertical incidence, so we don't have to worry about the angles at all, just for vertical incidence, so this is all 1. If we have velocity difference of say 0.5 kilometers per second, 500 meters per second, and 1.5, that's a ratio of about 3, and then you take the square root, and so that means the amplitude ratio is going to be about 1.7 across this interface. Density also comes in, but density does not change as fast as velocity. So velocities really are the main contribution. So that's a linear explanation of just why softer, low velocity sites tend to have higher amplification. So anyways, site amplification can be very strong, factor of 10 or more, very over very small distances, 100 meters or probably even tens of meters. And the lower velocity soft sites tend to have higher amplifications, and also, as John mentioned, from the H over V, resonances at around 0.3 to maybe 1 hertz. Okay, John mentioned several ways of measuring. I'm also going to talk about those very similar ways. Probably the most direct and most accurate one is just go out and measure the site response. So you drill a hole and you can measure the P velocities, you can measure the S velocities, you can measure the densities, you can measure the resistance, these what they call the blow counts. You can look at the structures, and you can theoretically use these values to predict the site response, but this is probably the most direct way to characterize a site. The problem is it's relatively expensive to drill a hole and to make measurements, and so it takes time and money. And as I mentioned, you want lots of measurements, maybe 10 meter or 100 meter, and so this is difficult to do at that kind of scale. Before these microseisms, the noise measurements became more popular. Probably the most, the way most people measured site response was using a relative method by putting a seismometer on a reference site, which was presumed to be a hard rock good site, and then looking at what other sites, other target sites for the same earthquake, which is coming in from some relatively far distances, and just comparing the seismograms at these two different sites. So you just take a ratio of your target site to the hard rock site, and you can get what is the amplification at these various sites. And usually you do it in the frequency domain so that you can see it as a function of a frequency where the which frequencies may be amplified or de-amplified. And this was a good way to see these peaks and the amplification, and a very straightforward way for saying what was the difference due to the site response. This was commonly used for aftershocks. It's a very good method. If you have lots of small earthquakes happening, you just put seismometers at different sites and you measure the same earthquake. And this was a very good way for evaluating site response. Lots of studies have done this. One thing though, this is, like I mentioned, good for aftershocks. But very often you want to know before the earthquake, not after the earthquake, what the site response is. And so if you don't have earthquakes happening, it's hard to do this kind of study. You can use maybe teleseisms or regional earthquakes, but that's a little bit more difficult. So these microseism methods, like John mentioned, the Nakamura method, are good because you don't need earthquakes. If you put a seismometer down any place, you always see something on your recording. It's not a flat line. You crank up the gain and you can see some kind of shaking. And this shaking can be used for measuring the site response. John also mentioned short periods, less than 1 second, are usually due to wind or traffic or machinery or cultural noise. Longer period of a few seconds is usually due to ocean waves. Even if you're far away from the ocean waves can still produce microsize in the middle of continents. So there's always recordings of seismic noise or seismic signals, no matter where you are, when you are, and you can use this sort of level of shaking to estimate the site response. And maybe I can skip this slide, but as John mentioned, it's a very simple method, this H/V or Nakamura method. You just simply take the time signal and you take the ratio of the horizontal spectra to the vertical spectra, and usually you stack over many windows to get a more stable measurement, and you can look at different stations. When this first was proposed back in 1989, it seemed like a very simple method, but I think many people didn't believe it. I mean, it seemed almost too simple. So there were many sort of studies comparing this with other methods. And so, for example, here's that period estimate, period estimate from the microseism, the H/V, compared to earthquake, compared to what I mentioned before, these sort of reference site measurements of taking the same earthquake at two different reference sites. And actually, and you can see that the period, determined by the microtremor, by the H/V, is very similar to the answers that were given by using a reference site. And so people made lots of these comparisons, and so they were very well convinced that the period was a good measure, that the microseisms were giving a good measure of the site resonance or the site period. John mentioned that the amplitude is not very good. There's, I think, maybe a slight cultural difference between the US and Japan, but people do believe the amplitudes from the H/V method in Japan, or at least have a little bit more confidence. And here's one study that shows the amplitude using reference site earthquakes and the amplitude using microtremor. It's not one-to-one. The microtremor measurements tend to give a larger range, but they seem to still follow the same trend. So if you make this correction in amplitude by, I don't know, a factor of 2 or something, maybe you can still use the amplitudes to, the H/V amplitudes to get an estimate of what the amplitude difference at a site could be from the H/V measurements. Okay, here's just another study from Europe measuring the H/V period versus reference site earthquakes over a much larger range, over a much larger data set. And again, people have a good confidence that the H/V is giving a very good measure of the period. So you have this H/V spectra, and it seems to give a very good measure of the site resonance or the site dominant period. And that's actually a little bit hard to explain. I mean, why would the horizontal to vertical spectral give you the site resonance? And people puzzled about this a lot. And I think there was not a very good explanation for many years. There's sort of a general simple explanation that you're measuring essentially Rayleigh waves. And as you know, a Rayleigh wave has a retrograde elliptical motion. And for low velocities, it has bigger amplitudes in the horizontal rather than the vertical. And for higher velocity material, the motion of the Rayleigh wave is larger on the vertical than the horizontal. And so thinking about Rayleigh waves, this measure of H/V is kind of a reasonable explanation for why it's giving you this period. But this was sort of a very qualitative explanation. And empirically, H over V seems to work very well. And it gives lots of good information. When you compare it to earthquake reference site information, it gives consistent results. But people were still very puzzled why it works so well. Recently, Sanchez Sesma in Mexico actually wrote a very theoretical paper explaining it in much more quantitative. This paper is actually pretty hard to read, and actually I don't understand everything in it, but he does present these kind of propagation theories and saying why they do a good job in explaining why the H over V method works for looking at site response.
How did Nakamura come up with the idea if there was no basis at first?
I'm not sure, but Nakamura is sort of a very empirical person. He's actually a very opinionated person. I actually know him, and I think he must have just seen a lot of this. Well, actually, I'll get back to this, but Aki proposed some sort of similar methods back in 1957. And not exactly the same, but in a sense, Nakamura is sort of a simplification of some of the ideas that Aki presented. And he started from there. Actually, I'll come back to that at the end here. As John mentioned, it's a very easy measurement. You can just measure it for maybe 20 minutes or an hour. If you have teams out there, you can measure hundreds of sites in a few days just by plopping down an instrument. It's easy. You can do it on roads or on the ground. You know, when you're putting out seismic sensors, you're always looking for low noise, stable sites. But for this, it's actually the opposite. You want noisy sites. And so it's a very easy measurement that you can make over many sites. Usually you stack windows, maybe 10-second windows over an hour or so. So you're looking at 200 or 300 windows. So that gives it a good stable measurement. And typically you're looking at frequencies from about 0.1 to 10 hertz, which means you're looking at wavelengths on the order of 15 kilometers to 150 kilometers. Okay, this is just a survey we did in Taiwan. Whoops. We measured, I think, 50 sites in 2 days with 2 teams, and we got very clear resonance peaks at different places. So up here it was about 1.5 hertz, in the middle it was about 1 hertz, and then down here it was maybe 1 hertz to 3 hertz. So a very easy, robust measurement, and it's being done very commonly all over the world now. Okay, John mentioned, what did he say? MASW method. I think that's very similar to what in Japan we call the SPAC method, the spatial autocorrelation method, which, as I said, was actually proposed by Aki back in 1957. And what it does is it looks at correlating microseism waves to obtain the phase velocity. And you assume again that you're looking at Rayleigh wave phases, phase velocities, and you can use a dispersion curve to invert for the actual velocity structure if you have the dispersion curve. And this is actually also a very powerful technique. And okay, let me just take a little bit of time to explain a lot of these noise correlation methods. So very simply, if you have 2 stations and you have a wave coming in, if you look at this wave at station A, it looks like this. The wave arrives at some time TA. At this station, it arrives at some time TB, which is later because the wave is propagating from left to right. If you take the cross correlation of these 2 signals, then you just get a spike at this time A minus B. I hope people know what cross correlations are. They are simply a way of comparing 2 time signals and looking at how they're similar and what the time difference is between the similarities. So you take the cross correlation and you get a spike simply at the time difference that it takes for the wave to travel. If you're looking at noise, you don't have a nice spike, but it turns out noise really is correlated, especially if you stack over many windows, maybe 100 windows, you really find out that there are propagating wave packets in the two noises. And if you take the cross correlation, you do get a nice spike like this that corresponds to the time difference of the propagation from station A to B. So this is one dimension. And of course, so if you do it in the opposite direction, if the wave is coming from right to left, and again, you have the same wave packets, you do the same type of correlation, you get the same type of answer, but now the wave packet is coming at minus 0.5 seconds instead of plus 0.5 seconds because it's coming in from the opposite direction. So very simple one-dimensional case. If we look at 2 dimensions, and so we have all these different sources that are, again, recorded at these 2 stations, you get all of these traces here. And again, these are just those autocorrelations of all these different sources. And what you see is this nice sine pattern. So at 90 degrees, which is these sources here, they arrive at the same time at the 2 stations. For minus 90 degrees out here, it arrives at this station first, and so you get positive cross correlations. For 270 degree azimuth, these stations arrive first at this station, and so you get minus cross correlation. So again, very simple, but in 2D you get this kind of pattern. Looking at it a little bit more closely, this is actually the same type of data, but these again are the cross correlations. This is azimuth, and again at 90 degrees, the cross correlation is 0. At sort of when it's coming from the left, it's arriving first at the station on the left, and at these stations, it's coming later. So anyways, what this figure here is adding up the traces, adding up all these cross correlations. And so if you add up all these time series, this is the pattern that you get. And it's obvious, not obvious, but it's reasonable that you look at this and you add up these parts here and you get this signal. You add up all these signals here and you get this signal. And when you add up this part here, it's not real clear at first glance, but they cancel. And so when you add up each of these traces, this is the figure that you get. You get the cross correlation of big amplitude coming from sort of minus 9, coming from the left, and this big cross correlation coming for the stations coming from the right. And the reason is, if you look very carefully at these waveforms, at these peaks, where they're coming from either the left or right, the waveforms are very similar. So they interfere constructively. But over this range of azimuths, actually, if you look carefully, the positive and negative peaks tend to cancel out. They sort of come at the same time. So over these periods, not periods, over these azimuths, the waveforms cancel. And so when you add up all the traces, you don't see much amplitude in the cross correlation. But at the 2 peaks, you see very strong constructive interference. And so you get that nice pattern where you only see the strong autocorrelation amplitudes at these azimuths corresponding to the horizontal contributions. Okay, so if you do that, And here's just an example of real data. If you take two stations that could be 1 kilometer apart or 50 kilometers apart, and you do these cross correlations, you actually get these two nice pulses, which correspond to the horizontally propagating phase velocity. And if you have a lot of stations, you can take all the different pairs. And if you take all the different pairs of stations and plot them by distance, you get this kind of nice picture. So this is a station spacing of 20 kilometers. This is a station spacing of 70 kilometers. And you see these nice, both the positive and the negative cross correlations. And this velocity, this trend, gives you what you're looking at, the 2.1 kilometer Rayleigh wave. So this is a very popular technique. It's used at all scales. And if you just measure noise, just measure the ambient seismic noise, you can see the propagating velocities. And so that's what we do on a very small scale. So in addition to doing the H/V measurements, we actually put out a small array at each site. A triangle array at sort of 60 centimeters, and then another one at 10 meters, and another one at an additional 5 meters, 15. And so we measure the noise at this mini array. And when we do that and do the analysis I just mentioned, we actually can see differences in the phase velocity as a function of frequency. So here's two different sites. This one, here's the dispersion curve, or here's the velocity as a function of frequencies from 1 to 10 hertz. And here's another site over the same frequency, which has lower phase velocities. So it's actually very surprising that you can get this kind of resolution over just a few meters, over 10 meters, if you measure for a fair amount of time and stack lots of data. And so this is what we did. And we can then take these dispersion curves and invert or do a forward calculation for what the velocity structure is at each of these sites. And actually, this is what Aki proposed in 1957. And there were a few studies then, but this method really caught on in the 90s when all these noise measurements came, and we could had many hundreds of noise measurements and measurements of phase velocities and then inverting. Okay, skip that. Anyway, so here's the result we got. So each of these lines, each of these stations, we had phase velocity curves. And so we calculated a one-dimensional velocity structure for each of those sites. And this figure just sort of pastes all those one-dimensional velocity curves together. And we got this nice velocity structure. This is the fault. This is a thrust fault. This is the hanging wall. This is the foot wall. And so this, the higher velocities here are reflecting just the offset in the fault. There's soft soils here, which are reflected nicely in these velocities. And these are the shear wave velocities that were obtained from about 1.5 to 4. So anyways, this is a very, very powerful technique. Or with relatively simple, frequent, dense measurements, you can begin to get some very detailed measurements of the near site. Okay, so I think I'll stop there. Again, just site response. We've been saying these same things over and over the last couple of days. Site response is important. You can get very large differences because of the local velocity structures and topographic structures. There's different frequency characteristics, different resonance frequencies, and the site response can vary over very small scales, maybe 100 meters or less. So if you really want to predict strong ground motions ahead of time, before the earthquake, or predict damage patterns, you need this information on a very small scale. For example, Japan has a probabilistic hazard map, which puts in the earthquake occurrence and the predicted probabilities of shaking. But right now they are trying to put together, they have, I don't know how good it is, but they have a site response map for Japan at the 250 meter scale. Actually, it's better in some places than others, but that's sort of in Japan, the kind of scale that they're working with to try to give the accurate ground shaking estimates. To measure site response, again, probably the best way is to actually drill a hole and measure the velocities and the densities and the kind of rock. If you can't do that, doing relative measurements from a reference site is good if you have earthquakes. If you don't have earthquakes, it's good to just use the seismic noise. The H/V is good for getting the dominant period, and maybe the amplitude, maybe not so good. But then if you do the same type of measurement using these mini arrays of several stations, you can actually get good estimates of what the velocity structure is. Okay, so I think I'll stop there then. Thank you.
Okay, thank you, Professor Jim Mori, for such an insightful presentation. And yes, as I said before, before the discussion, there will be some speech from Pak Supri, the Acting Director for Center for Research and Development. Yes, Pak Supri.
Okay.
Okay. Yes, Pak Supri.
Okay, thank you.
The floor is yours.
Yoshi. Yeah. Good morning, everyone. First of all, I want to thank to Prof. Walter and also for Dr. John Abel from Boston College and Prof. Jim Mori from Kyoto University. I have a message from Andri Dianugraha, Prof. Jim Mori. He sent best regard to you.
Okay, thank you very much. Yeah, I'd like to
Yeah.
see Andre again.
Okay, and thank you for Dr. Chris Parker from USGS and also Orifa Sativa, Ardian Yudi Oktantio, Dr. Sigit Purnomo, and also Robi Walansa. I think we already conduct the excellent training for the about 2 days. We take a topic about the ground motion analysis. BMKG or Indonesia need analysis of the strong motion data. So I think the topic, for example, ground motion prediction equation and also microzonation, very useful for us. But we have some problem about how to analyze the data. For example, for how to build the GMPE. I think still need more data and how to pre-processing the data before analyze. And BMKG also conduct the per view SR, or we call microzonation. But we still skeptic about the result because maybe almost all of my speech content of the question. For example, actually, what is the general assumption if we want to take analysis of H per R SR? And also, do we need special instrument or seismograph or we can use whatever the seismograph to conduct or to take the data for its per hour analysis. Can we use the short period or long period or broadband? Is it will give the similar result? And also, I think we don't have the standard method. For example, how long we need to take the data? 30 minutes or 1 hour? And also the grid, the size of the grid size of the when we take the data. And also actually when the proper time we take the data. Is it in the daylight or in the midnight? And also, is it need instrument need to remove instrument response before analyze the data? Or also, do we need also the station reference to analyze the data? And other problem, we also have the problem actually how to quantifying the uncertainty of the data of the result also. And also I still confused about the relation between the dominant period with the depth of the sediment, because actually the dominant period is also have correlation with the geometrical form of the sediment itself, not just variation of vertical velocity, but also lateral velocity. I think we also conduct the spark analysis and also the ANT, ambient noise tomography. Also, there is, I think, still some question about that, but I think enough for this time. And I think, Prof. Walter, we still have, or we still need the hand-on training in the future, how to analyze the data. And we hope that training can be held in Jakarta, and maybe Prof. Walter and also the lecturer can come to Jakarta in the next training. I think that's all from me. Thank you very much, Prof. Walter, and also all of the lecturer. Thank you. Mas Yosi.
Yeah. Okay. Thank you, Pak Supri, for the insightful speech and the question as well. Okay. Okay, ladies and gentlemen, now come to the discussion session. We have time until 9:50 for this discussion. So maybe before we start the discussion, maybe from Professor Muni, if you have any feedback regarding the Pak Supri's speech and questions, please.
Yes, thank you very much. And the USGS agrees with Pa Supri that the question of how to process the data and how to properly analyze the data, this is something to be done in the office, what we say hands-on. It cannot be done just by looking at a slide. You have to work together. So we agree with his suggestion, and we will move forward with this. Thank you.
Okay. Okay. Thank you, Professor Muni. Okay.
I have
Okay.
I have a question for Professor Mori. May I ask?
Yes. Yes, please.
So for Jim Mori and John Abel, you presented the situation of a layer over a half space, a uniform layer sitting on basement. But as we know, in some cases, it will be layer one of sediment, and then maybe a quite different layer below it, then the basement. Will the method give the correct velocities for layer one and layer two of the sediment, or will it average between them? Thank you.
You mean the observation or the theoretical calculation?
Well, can you retrieve two sedimentary layers, velocity 400 meters per second and below velocity 750 meters per second, and then basement? Or I think the ambient noise is going to smear. It's going to make a gradation. Rather than showing you two layers, it will show a gradient, because it's a surface wave method.
Right. And usually, so usually your observation, and I assume you're talking about the SPAC method right now, where I showed the velocities.
Right, right, that one.
Okay, so I mean, the data is just the dispersion curve. And just like in global seismology, we have surface wave dispersion curves. And then to go from that to an actual velocity model, well, there's lots of different methods. The most common one is usually just trial and error. You just build many, many different velocity models, and you just see which one fits. And so you're kind of a Monte Carlo type of method. So there's no guarantee that you're getting the correct one. What you're getting is a model that fits. And then, so you need to, you really begin to talk about uncertainties and how much resolution do you have in depth, how much resolution, which is probably the hardest thing for shallow measurements, how much resolution do you have at different frequencies. Obviously, the very long frequencies and the very short frequencies, you don't have very good resolution. So there's no answer, but what the best way to look at that is, of course, to do this where you actually know the velocity structure. Maybe have an area where there are boreholes and you can observe the velocity, right? And then do the same method and see how close they come. And that's been done, I don't know how well, but it's been done to some extent. And I think, generally the resolved velocity structures are probably pretty good, which means, velocity is good to, I don't know, 30, 40%. Depth's good to, well, that really depends. But I think these methods are fairly good. And, but of course, that has to be investigated. And if you really want very detailed information, you really need to put reasonable constraints on what you think you can resolve.
Maybe, thank you. That's a very good answer. Maybe, John, you could jump in here and offer your perspective.
Yeah, I personally think that this is a very fertile research question. And the reason why I say that is the following, so if you follow the original Nakamura idea, you're basically looking for a resonance in a soil column. And the resonance is going to be between some strong seismic impedance contrasting surface and the free surface, where you put your instrument. And of course, that the actual velocity is varying, going up and down as you go down through that soil column. But if you don't have any strong impedance contrast further up, the first strong impedance contrast is where you're going to get all your reflections. So it's inherently an averaging process. But Right now, with the Nakamura method, you make one measurement. You have this whole spectrum of information, but you're making one measurement. You're really getting one frequency and maybe information from the amplitude at that one frequency. But I think that there's probably all kinds of information at other frequencies that we're not modeling. For instance, the width of the resonance peak may have information about the subsurface velocity structure. You know, there are places where you'll see a peak, but then you actually get a trough at a higher frequency, and that trough is below a ratio of 1. And when the trough gets below the ratio of 1, I think that may be indicating, at least from what I've seen in the modeling we've done so far, that there may be a low velocity zone down somewhere in the subsurface. And of course, you know, from an engineering perspective, what do you really want to know? You really want to know what the strength of the Earth materials is. You want to know what the shear modulus is. So the nice thing is you're looking at something that gives you a lot of information about shear wave velocity, which is related to shear modulus. But if we can use other information in these H/V spectra besides just that one frequency, I think we might be able to tease other information out about the subsurface structure. But I don't think that, I think that that's a research problem that people really have to think about and attack, and no one's doing it yet. There was a question in the chat that I answered earlier about, well, what happens if you get 2 peaks? Well, that's a very interesting question, because I've got some data where I've got 2 peaks, and I don't know where the 2 peaks come from, and so we're going to try to do some modeling to see if we can't come up with a seismic velocity structure that gives us 2 peaks. The 2 peaks suggest 2 reflecting surfaces. Now, it might be 2 surfaces at different depths. Of course, it could also be 2 surfaces, one that's out of the plane, kind of like a side swipe, or what they would call side swipe in reflection seismology. So there's all kinds of things to think about here, and I think it's a fertile area for really open research.
Okay, thank you very much. I'm very satisfied with both of your answers. Maybe someone else has a question.
Yes, please, the participant, if you have any question, you can raise your hand to ask question directly to the speaker, or you can write your questions on the chat columns. Well, actually, we have several questions in the chat column, but it looks like Professor John Abel already answered it. Yep, Professor John Abel, please.
Yeah, I want to address a couple questions that Dr. Supri asked in his very provocative presentation, because, you know, he was asking, I think, very important questions about the method and how we advance the method forward. And for instance, one of the questions that got asked is how long we need to measure. Do we need to measure 20 minutes, 30 minutes, an hour, several hours? That's a very interesting question. I had a student measure once for 24 hours. We just got 24 hours worth of ground noise. And then we did spectral ratios. And it turns out that we got the same answer than if we had done 10 minutes of data. So very long stretches of time do not necessarily give you more information. We also discovered something very interesting when we did the 24 hours worth of data. We got much clearer spectral ratio peaks during the day compared to during the night. Now, why during the day? Because you have more noise. You have more cultural noise, for example, that gives you the sources at higher frequencies. You have more wind. So you're going to have a whole range of frequencies where the noise is higher during the day than during the night. So ironically, my opinion is that this method works much better when the environment is noisier during the day than it does at night. I know I made measurements once at a site which was right next to a bridge with all kinds of traffic going on. There were big trucks, there were cars. It was just every 2 or 3 seconds a vehicle was passing by. I thought, oh, this is going to be terrible. And I did the data, and they looked absolutely great. I got a very nice peak. It was right where I expected it to be based on what I knew about the geology. So in fact, you know, the Hvsr method and the ambient noise method, we would prefer to use in cities because those are the places where we want to know the most about what the site response is going to be. And that's where I think the method works the best.
Okay, thank you, Professor John Abel. Okay, maybe we have a question from Mas Pak Andri from Stagio Ternate. His question is to Professor John Abel: what factors should be avoided in measuring ambient noise for spark? Oh, I think it's for Professor Jimori. If I measure close to the beach, will it affect the results, even if there are hard rocks?
So as John just said, actually, high noise is better. So if you're near the beach, that's good because the waves provide lots of microseismic noise. The things that we try to avoid are, well, okay, there's sort of a difference between the H/V and the SPAC. The H/V doesn't care so much about what direction the noise is coming from. So you just want lots of noise. As John said, you know, traffic or anything is good for measuring the noise for the site. If you're using the SPAC method, you have to worry a little bit about if you have all the noise coming from one direction, because that will really bias. As I showed in the first example, you really want kind of a circular pattern of the sources, and the ones will cancel out and you'll be left with sort of the horizontal. But if you have all the noise coming from one direction, like if you have a generator that's operating in a factory close to your site and all the waves are coming from one direction, that does not give a very good result for trying to get the dispersion curve. It'll give a good result for the H/V, but not for the dispersion curve measurement. So if you really want to use these kind of detailed arrays, then you have to be a little bit careful about where your noise is coming from. You don't want it all to be coming from one direction.
Okay, thank you, Professor Jimori. So can we say that the SPAC is the local version of ANT, ambient noise tomography? Is it similar or almost similar or different?
Yeah, it's similar. Okay, so usually ambient noise tomography, they use the ambient noise to get the velocities between two stations. And then they invert those velocities for, say, a three-dimensional structure. For the SPAC method, we use the ambient noise to get a surface wave dispersion curve. And then we invert the dispersion curve to try to get the velocity model. So both methods use the ambient noise to get some kind of velocity information, but they're sort of different on the, what did I say, sort of the intermediate step.
Mm-hmm.
So for SPAC, you want to get the dispersion curve. For ambient noise tomography, usually what you want is the relative travel times between many stations over a big area. In a sense, it's the same information, but sort of that intermediate product that you use to get your final result is a little bit different.
Okay. Thank you, Professor Jimori, for the answer. So yes, we have to continue our. Yep. Please.
Okay, thank you, Mas Jesse. I would like to ask about the SPAC method, the spatial autocorrelation method, especially in the process after we got the dispersion curve. So the next we have to calculate to get the final result of the vertical profile of the depth and the Vs. Could you describe about the process from the dispersion curve to make the profile of the inversion process to get the final result of the vertical profile, Vs, and depth profile? Thank you, James.
Okay, that's a good question. And that's a common question in many aspects of seismology. 50 years ago, people were using surface wave, long period dispersion curves to calculate the structure of the Earth. And so for Spock, it's the same thing, just we're looking at a very small scale. Instead of looking at hundreds of kilometers, we're looking at meters. The theory is pretty much the same. You put in a velocity model and you can calculate what the surface waves should be and then what the dispersion of the surface waves should be. Usually you can do an inversion, but practically most people, what they do is they just generate many models, trying different parameters for the velocity and the depth, and then match those models with the observed dispersion curve. So it's sort of a trial and error or Monte Carlo method. And you could use some inversion techniques, but these data tend to be rather sparse. So lots of inversion techniques probably don't work so well. So that's why people use this sort of trial and error method where they assume a model, calculate the dispersion curve, and compare it with the observation and see how well it matches. Then do another model and do the same thing, and look at hundreds or thousands of models to see which gives the best result. Is sort of the typical way most of these research is done. Okay.
Okay. Can I get your email? Maybe we will discuss more detail to get the more material, maybe, or reference to we can deep learn for this matter.
Yeah, sure. I'd be happy to send you some information. Okay. We can talk. Yeah.
Okay. Thank you.
Okay. Thank you, Pak Sigit and Professor Jimori. Okay. We have to continue our session. We will start the last session on this course. It is from Robi Walansha and Dr. Sigit Pramono. Dr. Sigit is the coordinator of Earthquake Early Warning Division in BMKG, and Robi is his staff. And they will talk about Earthquake Force Design Ground Motion SNI of Indonesia. Okay, Dr. Sigit, you have time until 10:15. Yep, and then we can continue our discussion. Okay. Okay, floor is yours.
Okay, thank you, Pak. Okay, thank you, Mas Yosi, for this opportunity, and I would like to deliver my presentation. This is collaborate with my colleagues, Mr. Robi Walansa. Robi Walansa, is you already there? Pak Robi?
Yeah.
Okay. Maybe there's any problem with the networking because he's still doing the as the participant for the training in another training, the program in Egypt. Okay. Anyway, I would like to present about the topic related to the earthquake force design ground motion of SNE in Indonesia, and actually this the SNE refer to ISA of the US standard of the in America and United States, and we will present about the practically in this moment, but there is not discussed detailing or maybe what we do for the like the calculate of the we didn't calculate detailing with the maybe the detail in the formula, but we will use the reference from the SNA what we already done and what we already provided in SNI, so we can use that the reference to surface to the public. So whatever on or whenever we have to provide information related with the needs of the design of the structure, so we can do that, and we will provide the information as we BMKG officer, so we can do, and we will give the information to be in the reference by the engineer. As in the outline, we will talk about the earthquake and response spectrum, and then the earthquake force descent, reference of the SNI for 1726 2019. This the news on the updated the SNI. There is the last we talk about the steps to perform response spectrum analysis, and then anyway for this earthquake random ground motion, this the many direction we can get the information from the one source, and the way we can say this the many typical, because there is many condition like the subsurface condition will influence while the ground motion on the wave propagate from the bedrock to the surface. And we will talk about the how to get information from the PGA value on the peak ground acceleration in the bedrock, and then we will propagate to under the surface, and then we will continue to the building. So this is the very this is only the example for that condition about the propagation wave from the source until to the surface. And this the major damage to structure. Structure needs to be designed to withstand the earthquake ground motion. It should be survive if that the building is already calculated the worst of the earthquake release in the surrounding of that the location. So for example, maybe in one city on one location will build of the building, so we have to calculate the reference to probabilistic of the like the PSHA seismic hazard analysis, so we can get the potential or the probability of the magnitude most will influence or the more have to consider in one in that location, and then how many in the distance. So after that, so we can get the from the ground motion to be or become the one model, and we can get the information in after the in the bedrock, and then we can make the propagate or the reference of the amplification to get information in the surface. And we talk about the response spectrum in here. There is the simplified of the model of single degree of freedom. So we can say in the one building, actually there is many floor and there's many mode. So not only one type on one pattern will appear if the any motion or the big particularly of the big motion. But in this graph or in the response spectrum, there is only used with the approachment. So we will only use the description of the many mode become the in one mode. So this we can say this is the single degree of freedom. But if actually we will refer to the many modes, more than one, so we can say the multi-degree of freedom. And in here, there's the response spectrum, is scientific method for estimating the structural response. This is the dynamic vibration earthquake. And the response spectrum plot gives the maximum response for maximum displacement, velocity, or other parameters to natural frequency or natural period, subjected to specific excitation for linear single degree of freedom. Then the plot of this type is shown here in figure in what's one story. So you can say, sorry, is subjected in the ground motion, displacement indicated with the variable deflection. And the parameter affecting the response spectrum, so we using the same principle as time history, only instead of using the time history. So there's the many parameters like I said before. So there is any in the soil condition, and then the energy release mechanism, and then the damping, and epicenter distance, and the focal depth, and then magnitude. So this the many variable will involve to make the pattern of the waveform and or the time series. So this will let's say there is to be the whole pattern on the whole type of the response spectrum will appear in the graph, so we can see how pattern of the response spectrum information. This is the basic shape on the pattern from the response spectrum. In here, there's the many information. So this the relationship between the periods in the x-axis, and then the y-axis, this the spectral acceleration. So in here, this we can look in here, this and in the line blue line in here. So there is and in the this when the axis x-axis this is 0 or period is 0. So we can say this is in the value of the PGA. For example, in here, sorry. For example, in here 0.4. So we can say this the PGA 0.4. So when we see the period in period 0.2, so we can see in here this is the 0.2. So we cannot say PGA, but this is the PSA, pseudo spectral acceleration. In here, this generally in the SNA, we can say from the 0.2, this is the short period representative, and the 1.0, this is the long period. So in the code on the variable, we can look in here. This is as 0.2 surface and as 1.2 surface. So it's mean this the already information about the spectral acceleration, PSA, pseudo spectral acceleration in one period in 1 second, and then in here in the 0.2 second, 0.2 second or short period, and then the long period 1.0, and the PGA when the period is 0. So we can see in here the 0.4. And the formula, this is the approach, we can say relationship between the value when in information in the bedrock and then in the surface. So we can using the formula when use for the short period as 0.2 surface, the equal to FA times to for the short period, and for the long period FV. This is the FA, this is the amplification. So we can refer to the table 4 in SNA. This is the amplification value of representation for the short period. And then this is the amplification value of the long period. what it's mean about what the difference between the long period and the short period. This is related with the height of the building. So for example, 0.2, this is the equal with the second floor, or maybe the third floor or fourth floor. But for the high-rise building, so we can say using the long period. So until 10 floor, 20 floor, so this in the long period. This is the differences between the, we can say, short period and then the long period. So we can make imagine for the FA. This is the amplification correlated with if we need the information for the this only until the second floor, 3/4, and then if FV, this the related with the building of the 10 floor or more. This cover from the SNA, Standard National Indonesia. This the about the surface of the building, especially related to structure of the building of the bit of the building and then non-building. So this organization agency for Indonesia is already approved for this the SNA. So this have to be in the reference by the engineer to get the information to make the legally for or formally to make the structure or this design structure. So hopefully there's any the safe building and then the reduce of the victim when the earthquake happen. And this is the periodically change of the type of the SNA information. The first in maybe 2002, the information only divide in the zone, the 1, 2, 3, 4, 5, 6, yeah, 6 zone. If you want to say maybe for example in one city in here, maybe in Jakarta, you can see in here what color, and this is related with the value, the color. For example, is blue, so the color, the value, we can see maybe we have to make detail value, and for another city or another location, maybe in Surabaya, you can see in here the color in Surabaya, and the one color, this is the representative for the all type of the building. There is no any the significant difference if you want to build of the building on the dam, on the bridge. There is no difference. So there's only one in the one location. This the similar one value. But in the next time, so there is already divided with the using the spectral. So for example, if we talk about the building, like the houses or the office building until 10 floor or more, this is the building like in the surrounding of the our life. So we can use the map, the serial map for the PGA. So this information from the in the ground, and then there is already defined from the height building. For example, if we talk about the PGA in the floor 5 or floor 10, so we have to refer the different map. But in 2002, there is only one map, so we cannot say what the difference between the floor ground and then the floor 5 and floor 10. But in the 2012 and 2019 now, there's already in the difference between the we say in the ground and then we'll say in the floor height in the maybe, for example, the floor 5, floor 10, floor 9, this is the difference. So we have to using the difference map. And here, there is any the difference, the period. For example, for dam, this the longer. Then we talk about the ordinary building, because we know there's the dam. It's also not only for the short the time period, short the time life, but this is we have make the design from the dam is the longer. So the period time period for the calculate of the probabilistic seismic hazard analysis should be for that the period, long period. So the probably of we will get the PGA higher than we use in the short period. For example, maybe in the short period from the ordinary building, we can get the information in one location, maybe 0.2, but we talk about the design for dam, maybe until 0.9 or 1G, because this makes sense, because this the related directly with the lifetime of the dam. This should be concrete, should be dense, and I think this we will need the more budget. This is the very significant, but this the lifetime is longer than we talk about the ordinary building. This is the SNI for 17/26/2019. This we said before. So this any SDS, the descent spectral response acceleration parameter at short period. This one, and then ST1 in here, and then T the fundamental period of the structure, and T0 this 0.2 SD1 of the SDS, and TL long period transition period. This is the table we can reference in ISC2. This as well. This is similar. There's not much difference. This for will we define of the hard rock SA and the rock SB and hard soil for SC and stiff soil, and then the alluvium. So this the will determine which one the classified of the set class, so we can determine what type of the set class to make the correlate with the Hvs value, Hvs30 value. And this is the table. This is very important if we want to get the information in the ground, so we can see the amplification value. And in here, for example, from the top table in here, from the situs FA, this it means this correlated with the type of the situs, type of the set class, SA until SA, SF. This is the special condition. This parameter response factor for short period, 0.2 second, or S is. For example, if we already got information in the bedrock, for example, we in our location in here 0.4 in the bedrock, still in the bedrock, still in the bedrock 4. We need the information about the amplification, because I found this in my location. There is and in the sediment or the unconsolidated sediment in here. So we can make the correlation in the table in here from the short period from the SS 0.4 SS, so under the 0.5, and the set class SE, alluvium. So we can get the information of the amplification 1.7. So after we get information in the bedrock 0.4, and we want to know in the ground, after propagate you using the deposit soil in location, in that location. So we will get the value 0.4 times 1.7. So we can get information value of the PGA in the ground. This is the top FA for the short period from the not tall building. But this is the FE, so this from the long period. This is the same, so we can determine the probabilistics of the PGA in our location. For example, 0.2. 0.2 we can see in the column 0.2, and we looking for the reference of the set class, and we got the reference in my location SC. So 0.2 and AC, we got the information, the amplification 1.5. FV in the table, and the bottom in here, the table. So we can FPGA. So this is the information in the ground. So in the soil in ground. So for example, same. So we for example PGA 0.2, and we have information SB, so we can get the value constant amplification 0.9, 0.2 PGA, and then the SB, so we can get the information 0.9. So in here, in my location, we cannot say amplified the waveform from the bedrock, but this is the amplified, because this is the less than 1, and we have to times 0.9. So in the ground, the value is lower than in the bedrock. Yeah, I think this the cover before 2019 for SNI. For this the difference. I think it's the different building. As I told, this is the under structure maybe. And then there's the Australian International Assistant Bureau for Australia country. And this is I see the word. So how to get the information about the PGA or the PSA in the 0.2 period, or period is 1.0, or others, maybe 2 seconds, 3 seconds, or 4 seconds. We can use application from the RSA Cipta Karya. This is the already you can access using the website. You can see in here rsa.ciptakarya. So in Cipta Karya Public Works or pu.co.id 2021. This in here, this already information, we can input the coordinate on the name of the city, so we can show the result after we process using this application. So in here we can get the information of the Google Map, the original location itself, and then MCAG from the map for the magnitude consider earthquake in ground, and then the map MCER, this is the magnitude consider earthquake for the short period SS, and the map MCER for S1 is the map for magnitude consider earthquake for the long period. And then the map CR or CRS, this is the map for as the constant when we calculate the PSA in the short period. So we said we use the amplification. We have to once again times with this constant value for the short period, or as 0.2, we can use the map of CR. Sorry. And the long period on the high crash building, so we can see constant beside amplification. We have to time with the CR constant for the CR1. This is the step to perform response spectrum analysis. This sorry. Sorry, wait a minute.
Okay, sorry Pak Sigit, the time is already up actually, but you can continue for maybe 5 more minutes before we start the discussion.
Pak Robi is already attended in this discussion.
Maybe I will share screen my PowerPoint here.
You can continue for the next step.
Yeah, I will continue. Can I share screen my PowerPoint?
Yeah.
I will share screen. Maybe share screen.
Are you okay?
Yeah.
For your communication?
Pak Sigit, please, you can stop the screen sharing so that Robbie can start. Yeah.
Thank you. Okay, thank you, Pak Sigit, about the opportunity for me to sharing knowledge about the steps to perform. I would like to explain or sharing about the steps to perform response spectrum analysis for Indonesian area manually. And then first, to make the response spectrum, we need several parameters. It's the hazard map, and the hazard map is by Hvsr or National Standard for Indonesia, the latest National Standard for Indonesia. First, we have to select the location of the building to be planned. And for this example, we choose Pontianak. And then we have to determine the value for short period and long period. For short period, the period in 0.2 seconds, and the long period, the period in 1 second. And then for the Pontianak area, for short period, we have 0.25 G, and for long period, we have 0.1 G. And then we have to determine the amplification factor and the national standard available for cable amplification factor. And then we have to determine the set classification for Pontianak area or for your area. For Pontianak area, we choose hard soil. And then for application factor for short period. For short period, we have PGA at bedrock 0.25 G. And you can see the top table for site 5 hard soil, PGA 1.25 G, and we get amplification factor 1.3 times. And for long period, we have 0.
It looks like the connection is not stable. Okay.
Okay, maybe I will
Hello.
continue for
Okay.
this presentation. Could you start on your presentation? Mas Yosi, could you help for this?
Okay. Please, Mas Sigit.
Okay, this is the, is it clear, my voice?
Yes, you can hear clearly.
Okay, this we will continue, Mr. Robbie, because there is any problem with the connection. So this the continue for the when I said before this the formula, if you want to determine in for the short period, from the short period and the long period, when we already have the information about the PGA and the bedrock and the information of the amplification. And in the descent acceleration response of the SDS1, SDS-S, and then in period 0 and S, and from the TL to create the descent spectrum. So we can see in here. So for like in the left of the formula, and then in the right is the when we already inputted the value of each of the variable. And this is the TL map. This describe about this potential now many change of the value of the ground motion. So we can see in here, but this maybe not generally used, or many more used in the by the engineer, but generally only about the PGA and PSA for the short period and the PSA for the long period. This is the earthquake force descent from the submariner, for example. We can get the information like this, and the earthquake force descent, this the value this already times 2/3. So from the full scale in the 100 of the scale of the ground motion, but from the earthquake force we have to reduce, and we can get the value 2/3 of the ground motion value. So this is the peak of the earthquake force descent. This is the lower than the ground motion. So that's all of the my presentation about the spectral descent in SNA. So we can use the application using application from the public works application in RSA Cipta Karya, or we can use from the map of the Hvsr map. This already provided by the public works as well, and then we can use the information. But maybe we have to know, if we use in the Hvsr map, using the Hvsr map, this is the still the full value. There is hasn't divided from the third person of the value from the ground motion. So if we see in the application design of in the application, there is the value lower than we see in the map of the Hvsr map Indonesia. So I think that's all. Thank you. Maybe any discuss, please welcome.
Okay. Thank you very much, Pak Sigit, for your presentation. It is such informative and interesting and comprehensive presentation. Now we have maybe 5 to 10 minutes for discussion. You can raise your hand to ask question directly to the speaker, or you can write your questions on the chat column. Okay, please, if there is any question. Yeah, maybe if I can ask Pak Sigit, you said that the result from the application from Dirijen Cipta Karya is slightly lower than the actual seismic hazard. Is it true?
Yes, yes.
And is it how far it differ from the result of the application and the real hazard value?
Okay, thank you for your
yeah.
question. So we have we have to know, and we have to know about the define of the hazard map. The hazard map is the information about the PGA or the PSA after calculate using the degradation, and then the inform all the source, potential source, and then the information statistically, AB value and characteristic, and then the others. So there is no there is no including with the scope of the engineer, scope of the structure. So this is the originally of the calculate empirically, and then the probabilistic formula. So if we see in the hazard map, so this is the actual value after we use the formula and then the probability theory. But when we implement it in as the engineer, by engineer, so we have to consider about the ductility. This is the condition of the building. So we have to reduce the value in from the hazard map to consider that. So we have to consider the conditional of the building. So that the this the after we consider for like the ductility. So actually the value is the lower, should be lower. For example, before in the hazard map we can see 0.3. So if we talk about the design, the define of the design, this is or why we write the title. This is the not hazard map value. Why we didn't write the title about the ground motion value, but I put the title in this presentation about the force. This is we correlated with the design. If we talk about the design, we have to consider as we have to consider the engineering aspect. So this is the one part for that means we have to talk about like the ductility of the building, on the ductility of the structure. So we have to times not 1% like in the hazard map value, but we have to time 2/3 from the hazard map value. So we can determine finally of the design of the earthquake. I think something like that. Thank you.
Okay, thank you, Pak Sigit, for the comprehensive answer. Yes, maybe any question from the other participants? Okay. Okay. Maybe if there is no question anymore, it it finally come to the end of this course. Budona. Excuse me, Budona.
Yes.
Yeah. Okay. Okay. There's one question in the chat column to Pak Sigit. The question is, if we got T0 or dominant period from Cipta Karya application, then we calculate F equal to 1 divided by T0. Could we compare the value with the dominant frequency that we got from surface wave method acquisition at the same site? Yes, yes, that's the question. So please, Pak Sigit.
Okay, thank you, Reski, for your question. This is related for your question. If we got the null dominant period from Cipta Karya application, then we calculate frequency equal to 1 over T0. Could we compare the value with the dominant frequency that we got from surface wave method acquisition at the same set, same let along? I'm sorry, because this we have to know this different of the period value. This the period value related with the natural the natural period. So there is we didn't talk about the period of the medium. So this regarding for the period from the spectral acceleration. So we can see in the spectral acceleration. Sorry. Sorry. Yes, this is the period for related with the PGA value or the PSA value. There is not the define of the medium, but there is the correlated with the period when we correlate with the PGA in the ground, and then the 1 period 1 second in the floor 10 floor, and then the 22 second 20 floor. This is the initial value period value in engineering, and this is the we can approach of the like the what is it the variable or the parameter, for example, that's mean for the 1 second, this is the equal with the 10 floor, because this is the representative if using the approachment of the engineering judgment. So there is the number of the floor, we can divide 10 value. So if we floor 10 floor, so we refer to 1 second. If we have the floor until the 20 floor, so we have used the 2 second. So in the 20 floor, we have we can see the value of the PSA, pseudo spectral acceleration, or we can say PGA in 20 floor. So in here 0.1. In the 30 floor, we can refer to the period of the 3 seconds. So this is the model of the single degree of freedom. So this is the period defined related with the scope in the spectral graph, and this is the relationship between the spectral acceleration with the shape of the building. Shape of the building, in particular in here, related with the height of the building, height in the first floor, second floor, third floor, until high-rise building, until 100 floor or 50 floor. This is the high-rise building. So this is once again, this is the period. This is correlated with the model of the spectral acceleration. We can talk about in the frequency, it's okay, but this is not the frequency on the period medium, but the period on the frequency from the model of the building. And this means this related with the value of the acceleration, and then the height of the value itself, like the example before. So we talk about in the 10th floor. So in here we can see in 1 second. So how many the PSA? So we can say in here 0.2. In the 20th floor, so we can say in here PSA 0.1. Because in here we use the correlation between the period and then the number of the floor. Okay, I think this is our answer. Thank you.
Okay, thank you, Pak Sigit, for the answer of the question. Is there any more question from the participants? Okay. Yeah, if there's no more question, Bu Dona, can we finish this course and we do the closing ceremony now?
Okay, thank you for Mr. Yosi Setiawan to lead all of the session from the morning until now. So maybe before we are going to the end of the training, so maybe I give you a question for participant. Of course, maybe do you want to, if you have a, maybe you want to give impression or expression of the training, please, anyone to convey your feeling joining in this training. Maybe Mbak Enda Puspitasari, what's your feeling joining in this training from the first day until the third day?
But Bruna, maybe I have to close the presentation by Pak Sigit first.
Sorry, Mas Yosi.
Yeah.
Sorry, Mas Yosi.
Yep.
Yeah, can I ask to Muni? Hello, Muni.
Yes, please. Professor Muni.
Have you any comment about your design in United States about the period when how long to update, and then the implemented for this rule when the engineer have to regard for this regulation in the United States? So refer for the ISC regulation.
Yeah, I don't think there is any debate. I think there's good agreement on the standards and the criteria. So at the present time, we do not have any problem to report to you.
Okay, thank you, Muni.
Okay, thank you, Pak Sigit and Dr. Muni. Okay, finally we come to end of this course. I hope this course will be useful in our daily work, and I want to say thanks to all of the speakers. And
I have a final closing ceremony. I have final presentation.
Oh yeah, Okay, please, Professor Muni.
So thank you all for joining this important exercise. We were pleased to have 40 participants in the 3-day training course. And for the closing ceremony, I want to repeat the importance of strong ground motion and the recording of accelerations in Indonesia. We heard from Dr. Grace Parker that the ground motion models are complete for many other countries, and certainly Indonesia should be next. So here are the topics that we have discussed. I list just 6 of them, and I think we made a great deal of progress. So let's not forget that in California, not very long ago, a strong earthquake could destroy the critical infrastructure and bridges. This is from the presentation from Professor Jim Morey. And unless we have good data and good modeling, this kind of disaster could happen anywhere in the world that has not prepared for the ground motions. We heard several times from speakers, Ralph Archuleta, Jim Morey, and Grace Parker, that it's important for Indonesia to begin to plot the data that's available for moment magnitude on 1 scale going up to 8 and greater versus distance. This tells us how much information is available at a given time for which magnitude. And of course, people are very interested in this region here, high magnitudes above 6 and short distances closer than 2 or 3 kilometers. I want to thank the speakers who prepared so carefully, 2 talks each from Professor John Abel, Boston College, Professor Jim Morey today also, and Dr. Grace Parker, as well as Ralph Archuleta, or Oriza Sativa, who spoke to us yesterday, and today Dr. Sigit, who gave us his presentation. Thank you all for your time, and I know you spent a lot of time and effort to prepare your talks and try to make them focused and informative. Finally, everyone who participated was fully engaged and asked important questions. Thank you for your questions and for your participation. We will see you again at the next meeting. So let's work together to avoid future disasters. Again, a slide from Jim Morey's presentation. We hope that this kind of picture will never be taken in Indonesia. The organizers at BMKG have done a great job. Dr. Pa Supri, Bu Nelly, Florida Riyama, Bu Madonna, thank you so much. It's a lot of work, endless work in organizing this at the local level and at the BMKG. Thank you for everything that you have done. And with that, I'll say good morning. Time for you to retake the exam and then get prepared for your lunch. Thank you very much.
Yeah, thank you very much. It's a pleasure, Mr. Walter. So maybe for all speaker and participant, there's a regret from Buneli Furidariama. She cannot come to this session because she has a tight schedule, such as the leader. There's the leader meeting as well as the other meeting and coordination. But so for discussing for a couple of days ago until now, I have gotten the highlights. Maybe ground motion is very important to describe the hazard zone as the effect of the earthquake It can be realized in the PGR, spectral analysis, amplification spectra, and so on. Especially in Indonesia, the country with very source of the earthquake, like fault, the subduction, and the volcano activity. And then the research about the ground motion of each source is very interested, and it needs more development to give more detail of the earthquake hazard to the society, of course. And moreover, so I have reported to Bunelli Floridariama about the next training to improve the capacity of how to build a ground motion database for BMKG's employees, especially if people have responsibility related to technical seismology part. And she will be forwarding this recommendation, I think, to the person who has a role to make a decision. So overall, so thank you for all honorable speaker, and I do apologize if there are any mistake during training. And information for participants, please don't leave after a speaker session, because we will continue to conduct post assignment together. So thank you very much, Walter, and see you next.
See you next time.
Next time, I think. And thank you very much for Dr. John Abel, Professor John Murray. You are the great lecturer. And thank you very much.
Thank you, Jim. Thank you, John. You did a great job.
Thank you, everybody.
Yes.
Thank you, everybody.
And thank you very much, Pak Sigit and Pak Yosi Setiawan.
Okay.
Ya, buat Bapak Ibu, untuk post testnya sudah tersedia di LMS gitu ya. Ya, jadi silakan Bapak Ibu untuk menyelesaikannya. Saya beri waktu sampai jam 3 sore, tapi untuk pengerjaannya sekitar 20 menit. Ya, mungkin ada yang ingin ditanyakan terlebih dahulu. Nggak ada ya. Jadi nanti untuk pengerjaannya mungkin bisa langsung nanti setelah live dari live dulu ya. Nanti Bapak Ibu bisa mengerjakan masing-masing ya, maksud bersama-sama tapi masing-masing gitu ya. Jadi bisa. Kenapa ya Pak Ardi?
Materinya yang dari kemarin belum lengkap ya Mbak Duna.
Ya,
tadi hanya materinya dari PSGT aja satu saya lihat.
Iya, karena si Walternya itu dia akan mengumpulkan terlebih dahulu. Saya udah minta sih sama Walter gitu ya. Sebenarnya udah minta kemarin untuk minimal materi yang kemarin sampai dengan materi yang 2 hari yang lalu sudah dikumpulkan gitu. Alasannya sih kan buat ujian. Tapi belum mungkin nanti ya. Ya mudah-mudahan sih sesegera mungkin gitu ya. Memang agak susah sih kalau. Tapi sebenarnya saya udah kasih tahu ke udah informasi ke pengajarnya untuk segera mengumpulkan juga ke Walter. Jadi nanti Walter yang akan mengumpulkan, nanti dia akan share ke saya gitu ya.
Terima kasih Mbak Dina.
Jadi Bapak Ibu bisa segera untuk mengerjakan post-test, karena post-test itu kan menjadi sebuah nanti rekomendasi untuk mengeluarkan sertifikat gitu ya. Jadi ada alasannya gitu ya untuk Bapak Ibu untuk mendapatkan sertifikat. Ya, mungkin ada yang ingin ditanyakan? Ya, dari saya mengucapkan banyak terima kasih atas partisipasi Bapak Ibu semua gitu ya. Mudah-mudahan kita ketemu di lain waktu. Terima kasih banyak ya. Mungkin penutupannya tidak seformal dengan pelatihan biasa, tetapi semua prosedurnya sudah atas izin dari pastinya dari Kepala Pusat Pendidikan dan Pelatihan. Ya, terima kasih banyak untuk Mas Yosi dan Bapak Ibu semuanya. Ya, saya tutup pelatihan ini dengan alhamdulillahirobbilalamin. Assalamualaikum warahmatullahi wabarakatuh.
Oke, terima kasih Ibu Duna.
Ya, sama-sama.
aja.
Udah ditutup aja, ditutup udah selesai
N ya?
di end. Yang
Oke.
tadi.
Izin and meeting Pak Ibu semua.